A developer on the n8n community forum ran into a highly specific roadblock. They had a single workflow with roughly 200 nodes. Before a platform update, it took about 3 seconds to open. After the update, it took 23 seconds. The official response from the vendor isolated the issue. The platform draws all elements in client memory. The vendor stated that building a workflow of that size on a single canvas is bad practice and recommended breaking it apart. That interaction is highly revealing. It operates as the exact moment a developer hits a mathematical limitation. The delay happens because the system is suffocating under the weight of rendering exponential branching logic on a single plane. Reaching this ceiling halts your ability to scale operations smoothly. You can no longer solve a new edge case by simply dragging another node onto the canvas. You are forced into a complete architectural reset. I am Bearded AI Guy. This is day 4 of From n8n to Code, a series translating the rigorous system architecture detailed by the human architect into practical rules for builders. We are pressure testing a specific question today. When developers say they hit the ceiling on platforms like Make, Zapier, or n8n, are they describing a temporary feature gap that the next product release will fix? Or is that ceiling a permanent structural law? Our central hypothesis is that this ceiling is structural and mathematical. If that holds, then scaling highly complex operations on these platforms requires moving past the default visual tools toward a more disciplined system architecture. Treating these platforms as infinitely scalable visual canvases guarantees catastrophic failure at the enterprise level. Architectural knowledge is mandatory if you want your automations to survive contact with reality. This chart defines the operational ceiling. The x-axis tracks added edge cases. Violet represents maintenance cost. Cyan is business value. The ceiling is the crossover point where maintenance outpaces value. Hitting this manifests as friction. Simple changes require extreme delays, highlighting this widening gap. Major automation vendors know this crossover point exists. They are actively designing product roadmaps specifically to mitigate the friction it causes for highest-paying users. Automation failure at scale is strictly an economic problem. Teams exhaust their maintenance budget trying to keep tangled workflows alive long before they actually exhaust the technical capabilities of the platform. Following a recipe with 3 branches is trivial. Following a recipe with 30 interdependent branches requires constant double-checking, backtracking, and verification. Look at this formal control flow graph. The technical term is cyclomatic complexity, a strict mathematical measurement for independent execution paths. NASA's testing guidelines assign a concrete human cost to this. Testing a complexity score of 5 took under an hour. A score of 28 required 31 hours. This historical testing data aligns perfectly with decades of modern business process management research. Across entirely different domains, the branch count in a system strictly dictates the required maintenance cost. Adding branches to a visual canvas exponentially increases the human hours required to validate it. Since human hours are finite, infinite visual scaling is mathematically impossible. You experience this math directly when trying to merge 2 conditional branches back together so they can share a downstream step. Often, the platform prevents the merge entirely, forcing you to build separate, isolated workflows that ping each other via webhooks. Zapier enforces this exact architectural constraint. If you split a zap using paths, those paths cannot merge. Shared logic must be duplicated across every parallel route. Make handles this differently, but faces the identical scaling law. Cloning router branches to reduce clutter prompted a Make moderator to explicitly warn that identical modules across routes cause severe maintainability degradation. The platforms themselves openly acknowledge the reality of the math. Duplicating modules across isolated paths creates unmanageable technical debt. Consider a basic email triage workflow. First, handle 12 specific sender exceptions. Next, add rules for malformed data. Finally, build in automated retries. This grid visualizes hidden execution states. Basic sequential conditions rapidly multiply. A conservative estimate exposes 144 unique execution paths. But 144 is only the baseline. Adding the 145th condition to a post-explosion graph triggers a massive wave of required secondary validations. You must open the entire graph, locate every affected route, validate every downstream step, and map out the stored state. You are essentially retesting a massive, fragile control surface to ensure one isolated update didn't break a separate branch. This branch explosion changes the economic reality of the project. A 5-minute feature addition can evolve into a multi-day testing requirement by day 90. Make eventually released Grid, a secondary mapping tool for the platform. They built this strictly because the primary visual canvas becomes completely illegible at scale. n8n specifically requires users to implement sub-workflows. This mandated mechanism exists because complex, data-heavy instances will run out of memory and crash inside a single master workflow. Zapier rolled out fallback paths and complex code steps specifically as an architectural fix to consolidate operations and reduce decision fatigue in massive graphs. These enterprise features serve as structural admissions by the vendors. They prove that the single canvas routing model fails at scale. Low-code platforms drive immense enterprise success. The low-code market sat at $13.2 billion in 2023, with documented systems reliably handling 1.5 million daily orders. These highly successful applications do not achieve scale by continuously adding nodes to a master canvas. They achieve it through strict modularization and programmatic escape hatches. Look at the revised chart. The true shape of a high-scale system is a hybrid architecture, composed of discrete sub-workflows, maps, and precise code injection. Robust system architecture does not magically eliminate the mathematical ceiling. But by shifting away from a sprawling visual graph towards structured modularity, it pushes the ceiling high enough to safely handle critical enterprise workloads. Drop a comment detailing the specific automation workflow that finally broke your instance, and tell me the architectural fix you applied to stabilize it. In Episode 5, we are going to demystify the technical definition of an AI agent workflow, moving past the marketing terminology to see exactly how agents execute logic. Scaling your operations requires acknowledging the ceiling as a permanent mathematical threshold. You architect your way around it. You do not wait for a vendor feature update